Hello and welcome to chapter 2 of communication system. Okay, in this chapter we are going to learn about modulation and demodulation in amplitude modulation, or for short AM. Okay, AM modulation. Alright, in this topic, amplitude modulation is a modulation technique where the amplitude of carrier signal, the higher frequency, is modified by the lower frequency modulating signal, also known as information or input signal. So this is the earliest and the simplest form of analog modulation. Okay, from our previous block diagram, it shows that there is a modulator in both the transmitter and the receiver. Okay, this is used to change the input uh, to a different output signal. Okay, as you can see, there are the modulating signal here and the carrier signal, and change into a different shape. Okay, what that means is, so as you can see, the input signal is a sinusoidal modulating wave or sine wave. Okay, this is a sine wave, will change the shape of carrier signal. So this carrier signal in blue will change shape according to the red signal, which is the modulated signal. Okay, this carrier signal will change its shape following the modulating signal. Alright, in AM, this is the AM wave equation. Okay, starting from here, we are going to learn bit by bit about the equation and the calculation for this chapter. Okay, alright, let's say the modulating signal is sinusoid signal, and usually in exams it is usually in sine wave lah. There should be no changes in exams. Okay, so in this equation, you see here there are two different equations, but in actually EM is equal to VM. It might shows in the question, it might shows the VM equal to something or EM equal to something, but both of these are the same. Okay, so this is the equation, but usually this is not focused. Okay, this is also the same for carrier signal. So this is an equation for modulated signal. This is for carrier signal. Both of these equation, all these are similar. Okay, the only difference is the symbol for modulated signal is EM and FM or VM, but for carrier signal it's EC, FC or VC. Okay, so EC and VC is also the same if we are following this modulating signal equation. Okay, this is also similar, so it's easier to just memorize one of these, and others should be the same for V time here. Okay, alright, this is the AM wave equation because it can be expressed when both of these are combined. As you can see, this equation is for the modulating signal and this is for the carrier signal. But when you combine both of them together into AM envelope here, it has this equation where AM equal to bracket EC plus EM sine 2 pi FM time bracket close, and then all of this is multiplied by sine 2 pi FC time. Right? So this is the equation we get when we expand this equation. Right? It's EC sine 2 pi FC time plus EM sine 2 pi FM time sine 2 pi FC time. Okay, alright, please take note as you can see here from the theory itself, that carrier signal contains high frequency and the modulated signal is a lower frequency. Okay, so it should reflect on this also, where the modulated amplitude, peak amplitude here, it should be less than carrier EC over here. Okay, if EM is more than EC, distortion will occur. We will see some example of that later. Okay, so an AM modulator has two input. The first input is a sine wave with frequency of 500 Hz and amplitude of 1 VRMS. Okay, this is the amplitude. This is the frequency for the input. The second input is the carrier signal. Take note, this is the carrier signal with RMS voltage of 2 volts and frequency of 1.5 megahertz. Okay, this should be bigger than the first input. So determine the equation for the carrier signal, modulating signal, and the modulated signal. So after following this equation over here, we just add on this value into the equation. Okay, so this is the equation: EC plus AM sine 2 pi FM time, multiply all that with sine 2 pi FC time. Okay, so our EC over here is, where is it? I don't think it shows EC here. It only shows the value of FM, which is 500 Hertz for the input signal. It shows here 500 if for our FM, and FC is 1.5. So it shows over here. Since here it shows megahertz, you should change the mega into a numerical value, which is times 10 to the power of 6. Okay. So we will worry about EC and EM later on how to find that. So this is the modulation index, and this will determine the modulated signal later. Okay, the reason why we don't want EM bigger than EC is to avoid the distortion. Okay, so this is the ratio EM over EC. As we mentioned again, EM should be lower than EC. Alright, and to find the percentage, that value just multiply by 100. Alright, modulated signal can also be represented by M equal to Vmax minus Vmin over Vmax plus Vmin. So that value for Vmax is equal to EC plus EM, and Vmin EC minus EM. Okay, I think this is the solution for this. No, I don't think so. It should be this value, but I will look it up later. Okay. So this is the previous equation we have seen before on exercise 1 or example 1 over here. This is the main equation we should be looking into. But what if we substitute M inside this equation? Okay, it will change the equation into something new, which is from Vt equal to bracket EC plus EM sine 2 pi Fm time bracket multiply with sine 2 pi Fct. The value for EM over here will change into by using this equation. Okay, EM will be equal to M over M times EC. Alright, and then we pull out EC into outside the bracket. It will become EC bracket 1 plus M sine 2 pi Fmt multiply with sine 2 pi Fct. Right, so here is an exercise that you can try for AM DSBC envelope with Vmax equal to 40 volts and Vmin equal to 10 volts. Determine the peak change in amplitude of the modulated wave EM. Okay, and then find the unmodulated carrier amplitude EC, as well as the modulation index and the percentage modulation. Okay, do try this. I will put this inside the Google Classroom later. Alright, over modulation and distortion. Okay, for AM modulation index, M must be between 0 and 1. That is why I mentioned EM must be lower than EC. So this ratio letter, this division should not exceed the value 1 or 0. It must be between 0 and 1. Okay, if M is more than 1, overmodulation or distortion will occur. And distortion causes intelligent signal to become unintelligible. Overmodulation may cause the signal to occupy a larger bandwidth than normal. Okay, so this is 50% modulation, which is 0.5. So if 0.5, it is between 0 and 1, and this is normal. Okay, so here it shows 100% modulation, which is M is equal to 1. This is M equal to 0.5 and this is M equal to 1. So as you can see, when M is equal to 1, this sine wave will touch on the bottom part also, which cause some minor distortion over there where this part of the signal is missing. And if it's more than 1, as you can see from this diagram, it is 1.5 modulation. Okay, there is a small distortion over here in the middle where it overlaps the signal on the bottom and the upper part of the carrier signal. Okay, so let's go through the sidebands. The amplitude modulation process produces sidebands, and modulation by a sine wave will generate two sidebands. A more complex wave, voice or video with multiple frequency modulation will generate a range of sidebands. This one is no need to be worried, where we will only focus on one. Okay, to see the sideband, AM signal is viewed in frequency domain. Okay, this is the graph, the domain we will see mainly for sideband. So sideband with frequency higher than carry is called upper sidebands or FUSB, and the sideband with frequency lower than the carrier frequency is called lower sideband FLSB. Okay, there are two different frequency over here, which is frequency for carrier and frequency for modulator. Okay, so this follow back to the equation we see over here. Vt is equal to EC sine WCT. This is the carrier. Okay, and modulation times EC times sine WMT sine WCT. This is expanded using trigonometric identities. We will end up with this equation. Okay, so this equation represents the three different things, where EC sine WCT is the carrier. Okay, this is for the carrier, and MEC over 2 cos WC minus WMT, this is for the lower sideband. And here the equation for upper sideband is similar to the lower sideband, where the differences in the WC minus WM and WC plus WM. Okay. Okay, to find to find the upper sideband and the lower sideband, the question usually give these two values, which is FC and FM, the frequency for carrier and frequency for modulator. Okay, the FC should not be any changes, and this is the higher value for the frequency. Okay, but to find the upper sideband, FC is added with FM, and to find the lower sideband, the FC is read minus by FM over here. So that is the differences lah for the upper and lower sideband. Okay. Alright, the bandwidth for AM signal is calculated by B equal to 2 FM, and FM is usually given in the question. So bandwidth should be easier to find. Okay, so bandwidth is in hertz value, and the high FM is also in hertz. So bandwidth later will be represented by these two. Okay, the F upper sideband and F lower sideband. Okay, the bandwidth is also the difference between the upper and lower sideband. That is why I mentioned over here it is in between FUSB and FLSB, where B is equal to FUSB minus with FLSB. Alright, let us see with this example. An AM modulator has a maximum modulating frequency of 5 kilohertz. Okay, if the carrier signal is 980 kilohertz, find the sideband frequency and the total bandwidth. Okay, so sketch the frequency spectrum. There is a few things we need to look at here. So from the solution here, we are required to find the FUSB and FLSB, which is quite simple, where the F carrier will add with the F modulator, which is 980 plus with 5, which equals to 985 kilohertz. Don't forget the kilo over here because it mentions kilohertz, okay? And for the lower sideband, you just subtract the value 980 minus 5 equal to 975 kilohertz. Okay, we have found the upper sideband and the lower sideband. How about the bandwidth? Following this equation, there are two ways to find the bandwidth, which is B equal to 2FM and B equal to FUSB and FLSB. Here, we have already looked for FUSB and FLSB, so we just subtract those two values. Don't forget, the upper sideband must be the one in positive value while minusing the FLSB. 985 minus 975, which is equal to 10 kilohertz. That is our bandwidth. If we are using 2FM for our bandwidth, just use this value because this is your FM, right? 2 times 5 is equal to 10 kilohertz, which is similar. The same answer for the previous one, okay? Alright, the question asks you to sketch the frequency spectrum, okay? The frequency spectrum should be as simple as this. It is represented by x-axis on frequency, and the middle should be the carrier and the highest of them all. You should draw these three lines. The one on the right should be upper sideband because it represents the higher value, where Fc plus with Fm, we get 985 kilohertz, where the FLSB should be on the left, which represents the lower part of the value, where Fc minus with Fm, getting 975 kilohertz. You sketch this, you will already have 5 marks over here, okay? Alright, I think that is all. We will stop at this point of the chapter. In chapter 2, we'll continue back on our next chapter, which is for power relationship in carrier signal. Okay, that's all for this video. See you in the next one.